Today, I will get to how to correct or to attenuate the noise. That's what I want to do in today's class. Let's finish off what we did last time. We were talking about the various noises. We talked about the sources of noise. Talked about this noise, thermal noise. Then we talked about white noise, why it's called white. Thermal noise can also be called white noise because it covers all the frequencies. You can find that noise within any frequency. Now there is this question here. I think this is where I stopped, just to remind ourselves the rise time and the bandwidth. Notice we just defined the rise time last time, you know, the bandwidth. And there is a question that I want to start with, and it is handled very well in the textbook. I would use the textbook information before we move on to the next class. So notice this is a question which is in the textbook. It says, what's the effect on thermal noise of decreasing the response time of an instrument from 1 second to 1 microsecond? That question is in the textbook. So what is the effect on thermal noise of decreasing the response time of an instrument from 1 second to 1 microsecond? The response time is faster there, you can see. The response time decreases from 1 second to 1 microsecond. If that is the case, hope everybody has gotten the question down. Let's think through it, the way they handle the question. So what's the order in the change of the response time? From 1 second to 1 microsecond, how many times has the response time decreased? 1 second to 1 micro. Micro means 10 to the negative 6. So there is a difference. So it has gone from 1 second to a million, which simply means that it has increased or it has decreased by 1 million times, right? So that is the first thing that we need to be aware of in this case. Let's step back to our formula. The rise time is defined as the delta F, notice this is the bandwidth, right? Is equal to 1 over 3 times the rise time, right? So this rise time is related to the bandwidth, right? The bandwidth, as you know, you get it from the thermal noise. Remember the formula? U bar RMS equals to root mean square is equal to square root of, what's that formula? Look at it. 4K, where K is Boltzmann constant, times T, the temperature, times what? Times R, the resistance, because you are measuring that within an instrument, times delta F is the bandwidth, right? So notice those parameters. And what else have we forgotten? That's it.
What was bar again?
Mu bar is the root mean square, which is really thermal noise. That's thermal noise. If you go back, I'll go back, trace. So you can see that letter there, you call it what? It's a V. It's a V, yes. That stands for V, actually. That's a Greek letter for V. mu bar root mean square is equal to the square root of 4k t r times delta f. So you can see delta f is related to the rise time. All right? So that is what you want to get. And that's why it's asking for the change in the noise level. So what is the effect on thermal noise? Because what we are dealing with is thermal noise. So there is that relationship. There is the response time. There is the response time there. And now response time is related to delta F. So we have to know what delta F is. And so here is the assumption. If we assume that the response time is approximately equal to the rise time, it might differ a little bit on average, but we are just saying if we assume that the response time is approximately equal to the rise time, all right, we find that the bandwidth has been changed from, how do we get this? So we are assuming, okay, delta F equals 1 over T, 10 to the minus 6, 1 over, does that make sense there? So 1 over 3 times T, it has been decreased by 1 million. So 1 over 3 times a millionth, does that make sense there? Okay, so what are we saying there?
It's gonna make our bandwidth a lot bigger.
So this is the number we're getting here. Can you see that if you use 1 over 3, 1 second, that is 0.3 hertz. 1 second. Does that make sense? Per second. All right. And if it goes from this 1 over second, the rise time, then 1 over, all right, 1 over 3 times a second. Am I communicating to each one of you here? Do I need to write this? Delta F is equal to, what's the formula?
1 over 3 times the rise time.
1 over 3 times the rise time. And the rise time is, it goes from 1 over 3 times 1 second to, it decreases to 1 over 3 times 10 to the micro, did I say 10? Decreases to 1 microsecond, right? So 1 microsecond is 10 to the minus 6 of a second. Which got there. So 1 over 3 is 0.333333. And this other one here, 1 over 3, that is 10 to the 6th over 3. You notice that is 1 over 3 times a million, correct? And that is equal to 0.3. Getting to the bottom here. So this is 1 over 3 times 10 to the 6th, which is simply equal to 0.333 times 10 to the 6th. That is going to be 3.33. So those 3's times 10 to the 5th there. Per second. And per second means hertz. Frequency per second is what we call hertz. Okay. So this is per second, and that is 0.33. Again, I'm at the bottom there. Okay. So per second, 1 over a second is hertz. So this is what they're giving us here. Can we see that? It has changed from 0.33 hertz to 3.33 times 10 to the 5th hertz. Or now, if you look at those numbers, if you look at these numbers, if you divide one number over the other, they have not given. So this is 3. Same number. So if you divide this number over this number, it gives us a factor of 10 to the million. this is where we get this number. So what does that mean? This is a frequency. Per second is a frequency. And remember, in the thermal noise, it is a frequency bandwidth, right? So the frequency bandwidth, notice there, the bandwidth has been changed by a million. So delta F is a million. Does that make sense? Everybody okay with that? And if the bandwidth is a million, then we are dealing with the noise. Assume that the response time, we know how to get this. And therefore, what we are now saying, if I erase this, everybody is clear with that. You've gotten that right. So then the next thing is from this equation, which we know, notice this is the thermal noise, the mean square, the root mean square, this is the noise, is equal to 4kTr delta F. So we are going to assume that notice K is the Boltzmann constant. That's a constant. Then you know that you are operating at the same temperature. Might be micro and so forth, but for all practical purposes, the temperature doesn't change much. And what else? So this R is the resistor. We are assuming it doesn't resist. The resistor doesn't change much. So what we are saying here is mu bar. If all these are constant, then the only thing that is changing is the bandwidth. Delta F is a million, right? To the square root. That's the square root of a million, the constant there. And so what we're saying, and again, you can actually look at it this way. At this level here, there is the noise. And then everything, you divide everything, is simply a square root of a million. I don't know if I'm communicating that. When we go slowly. So at 1 second, you would calculate this. There are 4kT, we don't know that or not. So all these are constant. All I'm trying to reason with you is this is a constant. There is a factor of a million change in the bandwidth. And therefore, that simply means such a change would cause an increase in the noise by, such a change would cause an increase in the noise by 10 to the 6th, that's the square root here. Or the noise would increase the square root of a million is 1,000. It's going to increase 1,000-fold. So this is what these questions are about. It's keying you into what we know about noise. But more importantly is the relationship. It cements your understanding on the relationship between bandwidth and price. Okay. Any question here? Any other question? Yes.
Why is it raised to the half exponent?
Half is the square root.
Oh, okay.
Yeah, this is the square root. Okay. Yes, sir.
Is it always fair to say that the response time and the rise time will be about equal, or will there ever be like a difference in them?
It's the response time and the rise time would be equal. Why did you make that conclusion before I answered your question?
No, I've read it. Like I was saying, is it fair to
If we assume that the response time, we are just assuming. There might be micro changes, small changes in the resistance, but for all practical purposes, we are just assuming to give us the bulk conclusion on where we expect the noise to change by 1,000-fold, 900-fold, 800-fold, 1,001. It's around there. Okay. Because you understand, if you are working with an instrument, the resistance will not be always exactly. Okay, so that's what that is. And so we have dealt with that. And now I want to talk about short noise. Short noise. So when does short noise occur? Remember, what kind of noises are we talking about here? We have two types of noises. Temporal noise and instrumental noise. So all this that we're talking about are instrumental noises. Short noise is also part of noise. When does instrumental noise occur, and where does the instrumental noise occur? Any guess? And guess as to where short noise would occur. What do we mean by short noise? If you don't understand what short noise is, you may not be able to answer the question. All right. So what is short noise? So short noise occurs due to the movement of electrons across junctions. It occurs due to the movement of electrons across junctions. So p-n junctions. And so charged particles across junctions. And we're talking about the p-n junctions, those of you in the physics world. Positive, negative, poles, and whatever. So yes, essentially, we make it very simple. It's electrons moving from one point to another. Okay. So movement of charged particles across junctions. So that's where short noise occurs. And for example, in evacuated spaces between the anode and the cathode of electrodes, you are likely to see short noise. Or not likely, it's going to occur. It's not that. And so when does it occur? Where does it occur? We have answered those two questions. When does it occur? When we have electrons move across the junctions. All right. And where? We have when we have charged particles, where in p-n junctions. And if you have an evacuated space between the anode and electron, those particles can jump from one end to the other. But there is going to be some noise due to that. And so why does it occur? So this is a random quantized effect. Random quantized effect of the particles, electrons, and because of the statistical fluctuation of the electrons. And here is the formula. Formula. So you have I, random noise. I means anyone who can guess what I stands for on physics viewpoint. That's correct. Yes. Cause movement of electrons across junctions. That's correct. All right. So I, that is the current, which is root mean square, is equal to 2. That current. I want to define it correctly. So we want to define that correctly. So you can see there, we know delta F, don't we? And the E, the charge of the electron. So this is the short noise. Let's be clear. This I will be current. This is the noise. The small I is the noise. Small I is the short noise that we are talking about. This other one is different. Okay. So in the bandwidth and E. So we'd say it's a random effect, quantized random effect. This is white noise. Yes, sir.
Wait, so what is that?
This is current. This is the noise, short noise. And notice what we are saying there. White noise is the same at any frequency. White noise is the same at any frequency. Is it frequency dependent? It's not. It's not frequency dependent. Which noise is frequency dependent? flicker noise, right? So 1 over F. I think that's one of the questions that if you look at Topology online, I know you might be totally. One of them says define short symbols and the formulas if appropriate. Formulas of chemical noise if appropriate. Right? Instrumental noise, you define, might use words there. And then there is a third term on modulation. We haven't covered that. And the other one is discuss thermal noise. Everybody should discuss thermal noise. Correct. Right? You know the formula. You know when thermal noise occurs. You know when you can decrease thermal noise by playing around with the formula. Right? Remember mu bar RMS, that is thermal noise, equal to square root of 4K. 4K what, Alexandria?
Okay, T R.
So square root of all that. And so if you want to decrease thermal noise, you play around with the resistor, you play around with the bandwidth. What else do you play with? And the temperature, that is critical. So those three. So that's what discussing means. And you have a formula there. I'm going to learn. And then flicker noise, 1 over F noise. You can say it's temperature dependent, right? What does it depend on? Short noise, as we have said here. Then environmental noise, you may have to discuss. Go there, environmental noise. All right. So flicker noise again, any noise that is inversely proportional to the frequency, i.e. 1 over F noise. It's called 1 over F noise. This is when each one of us in some dose of physics. Some dose of physics in instruments, in this case. 1 over F. So this is frequency dependent. And in this case then, a flicker noise, 1 over F noise, and the frequency dependent noise, you can see 1 over F. Now, it is frequency dependent. Yes, sir.
So it's 1 over F, however, the equation for frequency is 1 over seconds. So wouldn't that just make it equal to seconds?
Yes, if you look at it from that perspective, 1 over frequency. Frequency is given in, what is frequency given? Hertz or per second? Okay. Per second. Frequency is given per second, which is hertz. All right. Thank you for keeping us in that thinking. So it's frequency dependent noise. Now look at the formula. Flicker noise is proportional to 1 over F. So if you write a formula, flicker noise is proportional to 1 over F. If this is the case, this is going to feature in environmental noise. Please make a note of this so that we understand that better. So if it is proportional to 1 over F, if the frequency is very small, what happens to flicker noise? Big, right? If the frequency is large, flicker noise is low. This is what this means. We're talking about flicker noise. So when do you expect to see a lot of flicker noise? At very low frequencies. And when do we encounter low frequencies? What are these low frequencies that we are talking about? And you give examples, for example, in our lives, when you encounter, or examples that may come to your mind. the radio waves. Yes, there will be radio waves. We'll talk about that. AM antennas, and then you will see how sharp it is or how continuous it is. All right. So in other words, let's make that good conclusion. At low frequencies, you have enhanced noise, and specifically flicker noise at low frequencies. Because if you have a number, let's give a number. If it's low frequencies, for example, 1 over, let's say 0.001. That's 1,000 times, right? If it is a large number, go the other direction, 1 over 1, it's 1. So if you go to 100, that's 0.01. So this is large. This is at low frequencies. And this is at large frequencies. I've given large. 1 is not large. Let's give 100 hertz. 100 hertz, that is 0.01. You can see flicker noise is much more evident. This is 1,000. At very low frequencies, you will see flicker noise. It's frequency dependent. This usually, the effect of flicker noise is there is a long-term drift in DC amplifiers. There will be long-term drift in direct current amplifiers used in instruments. And it is significant, notice, it is significant at frequencies less than what? 100 hertz. Very significant at 100 hertz. So this is the boundary here. Less than 100 hertz, you're going to see flicker noise. And you see, notice, let's not talk about in abstract terms. When you acquire some information, some signal in the lab, and you have signals we are talking about, whether it is a spectrum, because that's what we do often in the lab, that particular signal that you see may be a contribution from noise, from the instrument itself. So instruments have ways of minimizing the noise. Use the software, play around with hardware, or play around with software. And those of you who may be good at computing, right, writing software may have that advantage. Okay, so all I'm saying here, flicker noise is significant at less than 100 hertz. So the cause of flicker noise is not well understood. We don't understand it fully because instruments, we keep trying to understand how instruments work. So it's not well understood. Okay. Yes, sir.
These different types of noise, do they have a unit associated to them?
Yes. For example, thermal noise, what's the unit? It is volt. So if you look through the numbers, like thermal noise is volts, okay? The other one, I, what do you think it will be? It's amps, okay? Thank you, Mr. Stalin. Those are, yes, it is amps. Because if you look at those numbers, the units in the calculations, it comes out, they give you that. You can try that. Questions at the end. Okay, so now that brings us to an important aspect. Now, in flicker noise, help us move into environmental noise. Environmental noise. So how many types of noises we know so far? Chemical noise. The other one. Mental noise. And mental noise. This instrumental noise when noise is due to the composite. Composite, yes. So that's composite of noises from different sources in the environment. That would be top of my head. I do think put an animal down. Hold on a second. Anyone who has used an SCM, coming electron microscope, or a TM, those instruments you can't put them on top. Second, they need to be grounded to minimize them picking up the noises from the surrounding. Because as you know, the NMR, we have the wiring, the conductors inside, superconducting magnet. It's going to pick up any of the frequencies, and more specifically, it's going to pick up any of the frequencies. So we put it here on the ground. So we are saying here these are different sources in the environment that surround the instrument. Now, notice what that's the I like school. This section. I've done a good job as far as chemistry is concerned. And just to give us the information, you can go into more details in physics, actually. Please. So much environmental noise occurs because each conductor is in an instrument is potentially an antenna. It is capable of picking up electromagnetic radiation and converting it to an electrical signal. So whatever surrounds the instrument, the conductors, whatever wiring system. So it's going, those wires, remember what two signals that we get from an instrument is what and what? Voltage and current. So the wires are going to pick up, the circuits are going to pick up any of the disturbances, right, in the environment. So the noise occurs because each conductor in an instrument is potentially an antenna. You're going to pick up any change. And if it does, then it converts it to a signal, a voltage or current. Any questions so far here? So think about any instrument wherever it is placed. What are the potential sources of noise that affect that instrument? So there are numerous sources. Notice there is electromagnetic radiation, which is going to be picked up, converts it to an electric signal, whether it's very small or big. There are so many electromagnetic radiations. They can be magnified. There are numerous sources of electromagnetic radiation in the environment, including AC power lines, radio, TVs, and in our modern age, our phones, right? We all have them with signals. And so it will be interesting to see how well, I don't know how we can do it, however we can choose a particular frequency, how well our phones, you know, the phones have been, I mean, many people have had phones from, let's say 2000. That's when many people, everybody has a phone right now. I say everybody. So many people have their phones. So these phones interfere with the signals. Well know that in particular areas like military installations, they tell you to turn off your phone. Right? You go to a plane at a particular low before it takes off. What do they tell you to do? Turn it off. What are the other things? There are other sensitive areas. That means our phones can generate the noise. You can generate your noise, I can generate mine, and the conductors, whatever instrument will pick it up. Right? So that is what we are saying. There is something I want to present to you here on environmental noise. There are many noise sources from the surroundings. We've written that. This figure 3, I want to show you the figure 5.3, which shows the typical sources of environmental noise in a university lab. Think about it. If you have a lab in the morning, and students are coming in, or during the transition from one class period to the next, if you have your instrument, you would see it picking up this noise, environmental noises. And this was done, so I'll talk about those two quiet regions. The environmental noise is a good quiet region, 1 to 500 kilohertz, and a fair quiet region. So look at this diagram here. I hope it's clear. Remove that background. So notice environmental noise sources, not the frequency dependence. We talk about flicker noise. Notice the x-axis label. And you see the x-axis label there. Notice here, this is frequency in hertz a second. And you have 1, this is 1 here. 1. Then below 1, you have 10 to the minus 2, 10 to the minus 4, 10 to the minus 6, 10 to the minus 8. And notice here, what you're seeing here is, this is a power per cycle in arbitrary units. So you can see here, you see a peak here. This is pi. So this was done. Can you guess when this was done? Before many of you were born. 1968. This was done then. This with one I was reading this morning. Right. I was reading this morning about the person who did this was a very good analytical chemist. And his passed maybe in 2000. So his reference actually at the bottom of this figure. So he did this. And I wonder how he did it. So you see a spike here per minute. He says, this is an elevator. During those times, the elevators, there is noise. Right here per hour, change of classes, all right? Change of classes, the instrument picks up some noise. The noise here, temperature fluctuations per day, you have noise there. Then you have here per year temperatures. So what we see, we say here, this is environmental noise here. And then notice there are 2 regions in this environmental noise. So the sources of the noise, we have an elevator, classes, temperature, and anything that is going to be picked up by the instrument. That's what this is. I like this experiment because it was done long ago and captured all this. Then you have here, notice the 2 regions again. There's a fair quiet region here. There is here, notice the power lines at approximately 60 hertz and 180 hertz. What's the difference here? If you look at this diagram here. So look, you mentioned an AM radio, TV, and our phones around there. So what you see here is, this is a continuum here at low frequencies. But this environmental noise is continuous at low frequencies. When you come to these frequencies, 10 to the second, 10 to the fourth, you can see them, the numbers are given here. It's 10 to the sixth, 10 to the eighth. So we are talking about 10 to the eighth hertz per second. So this is radios, AM radios, and so forth. So you can see a sharp peak, very narrow bandwidth, unlike here. So that's the important thing. That should emphasize what we are talking about in environmental noise. I've given examples of instruments being placed at very low ground so that you don't have these drifts or the conductors, the circuits picking up the noise. So that's why we ground them. The same thing here. And so you see here, step back to quiet regions, a good quiet region, 1 to 500 kilohertz, and a fair quiet region between 3 and 60 hertz. And we have also said that in the region where you have a little bit higher frequencies, 10 to the 4th, 10 to the 6th, you usually get a spike, very narrow band. Unlike low frequencies, there's a continuum, and the noise is riding on the flicker noise. So that brings us to that. And now, I would want you to answer these questions on your own. Next week, Wednesday, I'll give you your first quiz. All right. So, and for your information, let me move forward. I think it's better for me to do that. I want you to go to the very end of the notes. Those are the questions for chapter number 5, 5.1, 5.2, 5.5, 5.7, 5.8. Most of those you can answer at this point, 5.9. And I've made a note here that all these questions are the same. The 6th edition, the 7th edition. I've tried to work with CMH, they're not responding to me, and I have to wait. What I want to do next, I will not go through this. I want to finish up on Monday with this. So there are two ways of minimizing noise, and one of them, too general, that is improving the signal to noise ratio. That means attenuating the noise. So two ways of minimizing the noise, two general methods. You work with the hardware and you work with the software. So first, you work with the hardware, that's instrumental design. The next one is software. For example, these days we work with computers or instruments using software. So hardware and software. Software based on computer algorithms, which is we use very frequently. These are the methods in hardware that I use for hardware. You have heard of this word grounding and shielding. Most of this is an art, it's not a science. So we'll talk about that on Monday. On Monday.
Friday.
Okay. Okay.